You're in.
Alright, hi. We're Team 65, you're the Waterloo Rocketry team. Not yet. I'm Hilbert, this is David, Miranda, and Ivan, and today we'll be presenting on our project for 2016 IREC. Next slide. So just a bit of overview about us. As our name suggests, we represent the University of Waterloo from Ontario, Canada, and our team consists of 15 undergraduate members. Our team focuses on developing self-built propulsion systems, and in recent years, we've been working on making a hybrid engine. So last year, our hybrid rocket, VIDAR-2, achieved liftoff, which was a major milestone for us, but unfortunately, it blew up in midair. So we'll be attempting launch with the next iteration of our rocket this year, VIDAR-3. Next slide. So our primary objective this year is to launch a redesigned hybrid rocket without destruction of the vehicle and achieve a safe descent upon recovery. We considered adding a functional payload, but in favor of a more conservative approach to our project this year, we've decided to just use a dead weight. So to sum it up, our objective this year is don't blow up, make a working booster, and we can go on to something fancy afterwards. So this is the layout of our design this year. Going from left to right, we have a slip-on aluminum fin can, which slips onto the combustion chamber, located underneath the oxidizer tank. So this makes up our booster module. Above that, we have our single-bay recovery module containing all the parachutes and the lines, followed by the Avionics module, which controls deployment, and then the nose cone and ballast. Next slide. So our overall design approach uses a modular monocoque design. So we use an aluminum structural skin for the airframe of the booster module, and a fiberglass airframe for the recovery and avionics. And we have machined aluminum couplers between each section for easy assembly of the rocket and disassembly. The rocket stands at 4 inches in diameter. We don't have it here because it's currently at the launch site. It's 130 inches long, with a dry mass of 52 pounds and a wet mass of 65 pounds. Next slide. So in terms of propulsion, it's been largely unchanged from last year. We're still using nitrous oxide and HDPE as propellants. From our most recent static test, we're expecting a peak thrust of 460 pounds, burning for around 11 seconds. Next slide. So the combustion chamber is made of 4 major components: the nozzle, fuel grain, igniter, and then the combustion chamber itself, which is a 1/4-inch aluminum tube that houses all of these components. The fuel is casted using 90% HDPE and 10% aluminum in a star-shaped pattern, which has proven to be successful and sufficient for our engine design. The fuel is casted inside an ABS tube, so both the tube and large amounts of unburnt fuel insulate the engine. And we haven't experienced any burnout. The nozzle is manually machined from graphite using a conical approximation, and all interfaces are lined with a flame-resistant caulking and O-ring sealed at the end. Next. The oxidizer tank is made of 3 components: the injector bulkhead, run tank, and vent bulkhead. So the run tank is constructed using an 1/8-inch aluminum tube and is capped on the ends using these 2 bulkheads, which have redundant O-ring seals. The injector bulkhead serves 2 major functions. Firstly, for filling. So we have a check valve inside the bulkhead, which can be attached to a fill port on the outside, which we use to fill a rocket from the supply tank. The second function is the ignition and feed system, which I'll touch upon in a later slide. The vent bulkhead contains a permanently open vent hole and a dip tube to regulate tank pressure and give us visual confirmation of where the liquid level is in the tank, and also allows us to abort the flight in case any emergency arises. The tank is designed for 750 psi with a factor of safety of 3, and has been hydrostatically tested to at least 1.5 times the operating pressure. Next. So the ignition and feed system. So our engine uses a custom pyrotechnic valve for separating the oxidizer and combustion chamber propellant. So the oxidizer is separated from the combustion chamber using a piston and an O-ring seal, and this piston is kept in the seal with a combustible pellet underneath. And this pellet is retained using the injector plate. So upon ignition, the yellow up down there will burn, and the pellet will burn as well. And as the pellet loses mass, the piston will displace downwards past the O-ring seal and open up the oxidizer channel. One major disadvantage to this design is that it takes a really long time for the valve to open up. So Similar to last year, if we press the ignition button and nothing happens for 30 seconds, it's normal, probably not an hang fire. Next slide. So we used a very similar pyrotechnic valve design last year in VIDAR-2, and as you know, that blew up. We're attributing the root cause of the explosion to backflow of combustion gases through the oxidizer channel into the run tank. The exact cause of this backflow is unknown, or cannot be determined with certainty. But in our redesign, we focused on the root cause, which was the backflow, and attempted to eliminate that. So our redesign emphasizes the importance of small, predictable changes during iterative design rather than large changes that may introduce many new variables and unknowns. So comparing our old ball pit to our new one, you'll notice that the oxidizer channel in the circle now has a lip machined into it. So in case of any back pressure, the piston will not be able to shoot all the way up into the run tank like before. Instead, it will be restrained by the lip, and this would seal the channel from any further flow and any combustion gases. So this is kind of our auto-save system for this year. Next slide.
Alright, our electrical bay consists of a fiberglass tube with aluminum couplers on either end, and inside is an aluminum sled to which all of our components are mounted to. The first is a 900 megahertz GPS transmitter for tracking. We have 2 commercial Raven altimeters, each with its own 9-volt power supply, and each is toggled on and off with a magnetic switch, which is toggled when you pass a strong magnetic field over the switch. The Ravens control E-matches, which are used for our recovery events.
So the rest of our recovery system consists of 3 parachutes. We have a dual deployment, and that's in a single bay. So the first deployment is our drogue parachute that deploys at apogee, and the mechanism for that is a CO2 injection. So with CO2 canisters and shear pins just underneath the Avionics bay, we can energetically split apart. The second deployment is our 2 main parachutes at 1,500 feet. And the mechanism for that is a modified 3-ring release with pyro cutters. And by modified 3-ring release, we just mean it's a 2-ring release instead. The reason that we have 2 main parachutes is simply because before competition, or as leading up to competition, we had a different design for our recovery where the rocket would actually split entirely apart and the main parachute would carry only the booster. And then as we approached competition, we changed our recovery design. So rather than redesign and refabricate one larger parachute, we just fabricated a second one of what we had already designed. But as you can see, the 2 parachutes are going to allow us to descend at a safe speed. So in terms of tests, we've done 5 engine tests in total. 3 of them were static inverted tests before last year's IREC. Our flight test was our explosion at last year's IREC. And then since then, we've also done one more inverted static test just to get some updated thrust data, as you can see up there. And then in addition to those tests, we've also, of course, done our hydrostatic pressure testing, as well as testing our recovery mechanisms, and it all is within the constraints of IREC. So our predicted flight, up here you can see the data that we've gathered from our open rocket simulation. One thing that is most notable about this is that our target altitude is actually between 10 and 12,000 feet. And as you can see up there, we're going to be a little bit higher than that. Based on our prediction, it's closer to 18,000 feet. So the reason that this could be is because when the engine was designed, we did not have a specific rocket mass and drag in mind at the time. And what's important to note as well is that considering we have not been able to successfully launch and recover, at this stage, customizing our engine to get us to our target altitude is not our main priority. As Wilbert said before, we first want to get a working rocket that doesn't blow up in the air, and then we think about things like that afterward. But once again, too, this is our best guess. It's a good estimation. But this year, if we're able to successfully launch and recover, we'll be able to see how well this simulation was actually able to predict our flight. And last but not least, thank you very much to our sponsors who made it possible for us to be here for today. Thank you very much for your time and attention, and we'll open it for any questions.